Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. In today's lecture, we are going to be discussing interesting class of compounds which has immense historical importance, particularly with respect to the understanding of transition metal organometallic compounds in general. These compounds that I would be talking of are called the sandwich complexes. These sandwich complexes actually refer to homoleptic or heteroleptic organometallic compounds. These transition metal compounds contains cyclopentadienyl or other kind of cyclic ligands that sandwiches or binds the metal or transition metal. This sandwich complex sort of originates from Ferrocene or has its genesis in Ferrocene and has aroused tremendous interest right from its synthesis to isolation to understanding the interaction that occurs between transition metal and ligand in sandwich complexes in general and that of Ferrocene in particular. A tremendous amount of enthusiasm surrounded this sandwich complex. Now, in our earlier discussion, we have seen how the sandwich complex can be very general, that it is not only limited to or restricted to cyclopentadienyl ligands, that it can vary from a wide bunch of ligands which can be cyclopropynyl cation or cyclobutane, cyclopentane, 6-membered, 7-membered, 8-membered rings. And we have also seen in our last discussion that sandwich complexes are again no longer limited to or restricted to iron. It can go all across the period starting from titanium, chromium, iron, nickel, cobalt, so on and so forth. So, as a result of this larger interest on these kind of sandwich complexes, there has been a tremendous growth in information available about them, and we are going to discuss today the variety of transition metal sandwich complexes that exist. Now, having said that even though there is a large body of compounds which fall in the category of sandwich complexes, there are also another interesting subclass of compound which arouse beside the sandwich complexes, and these are called half sandwich complexes. As the name suggests, that it contained only one cyclic ring and the other half of the metal is bare and bound to other kind of ligands. So, here we have a 6-membered cyclic ring bound to molybdenum in this half sandwich compound, and then the molybdenum in turn is bound to 3 carbonyl groups. So, this kind of complexes are called piano stool structure. As the name suggests that this resembles most likely the piano stool, where the six-membered ring sort of represents the flat seat of the piano stool, and the CO groups represents the legs of the piano stool. This also is a stable compound. As you can see that this is a 18 valence electron compound, 6 from the benzene ring, 6 from molybdenum, and 3 COs with 6, giving a total of 18 valence electron count. One can have the cobalt version of it, which contains a Cp cobalt and 2 COs. So this is a 18 electron complex. So 5 electron from Cp, 9 from cobalt, and 4 from CO. Again, this is the 18 valence electron compound. Now, as one goes from molybdenum to cobalt to nickel, again with a Cp ring, this is called a milking stool configuration. And this also is a 18 valence electron compounds. So one sort of sees in the pretext of the sandwich complexes that half sandwich complexes can also have versatility not only in structure but also in the metals which exhibit them. So it also can span according to across the periodic table. There are various kinds of rings that can get involved in formation of these half sandwich complexes, and also there exist various kinds of ligands which also can be part of half sandwich complexes. Similar to what we had observed in case of sandwich complexes, that there is also a similarity in the case that most of these complexes are electronically saturated, because they are also 18 valence electron compounds, similar to that what we had observed in case of half sandwich complexes. There is another interesting compound which is even extension or further extension of sandwich complexes, and these are called multi-Decker-sandwich complexes. So here it's a Cp, nickel, Cp, and again nickel, Cp, and it's a cationic in nature. So what is interesting over here is that the central cyclopentadienyl anion binds to 2 nickel on both of its sides or on both of its faces. So that is an interesting aspect of the cyclopentadienyl ligand in a triple decker sandwich, because this also exists or exhibits the property that Cp not only can bind to metal on one of its side, but in certain cases the CP ligand can also bind to two metal centers across both of its sides of the cyclopentadienyl anion. So that is a very interesting observation which comes out of it. Also, please note the fact that this overall compound is monocationic. That means that both of the nickel are 2 plus divalent cationics, which gives to 4 positive charge, and there are 3 anionic CPs, which is 3 negative. So 4 positive, 3 negative. So there is overall a positive charge to the overall triple decker sandwich complex. So this is just a vertical growth of the sandwich complex across the z direction, in which one can conceive this triple decker complex as being a nickelocene getting extended by another nickel CP unit on one of the face of the cyclopentadienyl ligand. So that makes this compound kind of very interesting. The most of the geometry that we have been considering about sandwich complexes is the fact that it seems that the sandwich complexes are kind of linear with two planar cyclopentadienyl ring completely engulfing the transition metal from above and below. However, as the portfolio of sandwich complexes expanded, interesting observation further came into being is the fact that there are lot of sandwich complexes which was even tilted in nature, and that these two CP rings are no longer planar. So these particular kind of ligands are called tilted sandwich complexes. So here is the example of pentamethyl CP, samarium, or bis CP molybdenum carbonyl, or bis CP tungsten dihydride. So these are an interesting variation of sandwich complexes, as one can see that these two CP rings are not parallel to each other and they are tilted across the metal. Another interesting observation comes from the fact that these at least the examples that we have discussed, all of them had second row or third row transition metals which are more bigger and bulkier than the first row transition metal, which most likely would show a normal sandwich structure, whereas the second row and third row, these are bigger atoms, where as a result the CP cannot fully engulf the metal center, and as a result they can tilt over and accommodate a third or the fourth ligand to make up for the increased wide space that arise because of the bigger nature of the central metal atom. There is another interesting class of compounds which contains more than 2 CN-HN ligands, or 2 types of CN-HN ligand. These are really very interesting compounds, and we will illustrate this with example. So we have Cp titanium so this is eta 5 Cp2 eta 5 Cp2 eta 1 Cp2 titanium. So the formula is eta 5 Cp2 eta 1 Cp2 titanium. So here we see that 4 cyclopentadienyl ligands are engulfing the transition metal. However, all 4 are not bound in the same fashion. They are actually bound in 2 different kind of fashions. One is eta 5, another is eta 1. The reason primarily probably is because of the fact that titanium being very small, all 4 cannot bind in a eta 5 fashion. It would be too crowded to do so, and so 2 are bound in eta 5 1 and 2 are bound in a eta 1 fashion. Similarly, with zirconium, there are 4 Cp ligands, similar to what we had seen for titanium. But what is interesting is the fact that zirconium, being a secondary metal, is probably slightly more bulkier than titanium, and as a result we see here is enough room for 3 Cp ligands to bind in a eta 5 fashion and 1 in a eta 1 fashion. So unlike in titanium where there were eta 5 Cp2, in this case what we have is a eta 5 Cp3, and instead of 2 eta 1 Cp you have 1 eta 1 Cp is zirconium. Now if one go down further to more bulkier elements, one can sort of see that one can even have ligands which have 4 eta 5 bound Cp, for example in this uranium complex. So this has 4 eta 5 bound Cp. So apart from the fact that as one goes down the group, the propensity of having larger number of eta 5 bound Cp increases, the other interesting aspect which these series of 3 complexes highlight is the fact that Cp can bind in more than one ways. It can bind in eta 5 as well as eta 1 fashion. There are also certain reports that we had seen in our earlier class where we had seen that hydrogenation of a nickelocene complex led to formation of eta 5 bound Cp and eta 3 bound Cp to nickel. The binding of Cp to metal is very much dependent on the size and the electron richness of the metal, and also the number in which the number of Cp's would bind in eta 5 fashion or eta 1 fashion is also dependent on this criteria. We are going to now take a look in some of the very interesting class of rings which are C3R3 or cyclopropyl ring based ligands. These, for example, PH3C3 plus cyclopropenyl cation, are important class of ligands which are aromatic. These obeys Hückel's rule. What is Hückel's rule? Hückel's rule says that if it has 4n plus 2 pi electrons, then they are aromatic, and in the present C3R3 plus n equals 0, so they have 2 pi electrons, and these kind of C3R3 plus cation compounds were first synthesized by Professor Ronald Breslow in 1957. At that point, it was a very interesting example of an aromatic compound having only 2 pi electron, and that the experimental proof validation of that was provided by Professor Ron Breslow way back in 1957, and hence this discovery is considered very important, not only then, even now from a historical perspective. We are going to take a look at some of the reactions which are involved in preparing these eta-3 cyclopropenyl complexes. For example, the reaction with PH3C3Br plus nickel tetracarbonyl under reflux conditions, oxidative addition occurs between on nickel, which is in a 0 complex states, and this PH3C3Br cyclopropyl cation, giving rise to this beautiful cyclopropyl cation phenyl nickel bromide, which is bridging to nickel carbonyl bromide, and this compound. This was synthesized way back by Kettle in 1965. Another interesting example involved the reaction of a nickel C3PH3 compound of nickel having bromide, pyridine with thallium Cp in benzene at room temperature giving Cp nickel C3PH3 cation. This also is a 18 electron compound, 5, 3 and 10, 18 valence electron compound. So, kind of stable, and this one also is 3, 10, 1, 2 and 2, 5, 15, 3, 18 valence electron compound. So, the distance between nickel carbon is 196 picometer and distance between C is 143 picometer. This was synthesized by Rausch in 1970. So, with that I would like to summarize what we have been discussing in today's class. Mainly we have looked into various kinds of sandwich complexes that exist. Not only the sandwich complexes, we have looked into what are the type of half sandwich complexes that exist, which contains one cyclopentadienyl or one cyclic ring apart from other ligands. We have also looked into various kind of sandwich complexes which sort of originated from Cp, whether they are homoleptic and heteroleptic, or the kind of variations they show along the rings as well as along the metal center, metal across the periodic table. One thing for certain, or which most of the sandwich as well as the half sandwich complexes that exhibit, is the fact that most of them or almost all of them are 18 valence electron compounds. So that means they are kind of stable once formed. We have also looked at various variations of half sandwich complexes or sandwich complexes that we have seen. This can be two Cp rings, cyclic rings being planar, which are normal sandwich complexes, or they can be tilted sandwich complexes or bent sandwich complexes. There are compounds which contains more than 2 Cp rings, and the nature of the Cp binding to the metal can vary from eta 5 to eta 1. As we had seen in this discussion, we had also seen eta 3 bound Cp in our last lecture, and also we saw that as one goes down the group to bigger and heavier transition metals or lanthanides, then one can see that these more number of Cp is being bound to the metal in a eta 5 fashion. We have also seen that how these compounds are synthesized. The first of its kind was synthesized by Professor Breslow way back in 1957, and then the kettle synthesized using oxidative addition route, which we had discussed by reaction of PH3C3 bromide with nickel 0 tetracarbonyl compound using oxidative addition step, and then a very elegant example in 1970 by Rausch, which involved reaction of a cyclopropenyl nickel compound with thallium Cp, giving this sandwich compound, which also is a 18 valence electron compound. Now, with this I would conclude today's lecture. We are going to look into the sandwich complexes, their reactivity, synthesis, and the variation in a bit more detail in the next lecture, which is following up on this. And thank you for being with me in this lecture, and also look forward to the next lecture, where we are going to take up the sandwich complexes in a bit more details. Till then, goodbye and thank you.